Okay, in this unit, we're looking at electrostatics. We're going to look at some basic intro information. We're going to see charging by friction, charging by induction, and charging by conduction. And at the end of this lesson, you'll know the difference between the three. So what is electrostatics? It's going to be the physics that deals with interactions of static, which are non-moving charges. So what you see here, each object individually, that object, and that object, they all have charge on them, but the charge itself is not flowing off the object or to the object. It's just staying on that object. So it's static or not moving, and that's the science of electrostatics. And we have positive charges, like this positive charge here, and it's going to attract a negative charge, which you see going on right here. This positive and this negative, they're attracted to each other. When released, it's going to flow towards it and start accelerating because there's a force going on there. And they're going to, positive charges repel other positive charges. So if you take a look at this side right here, this charge is trying to go away from that positive because it doesn't want to stay together. And if you had a negative charge, it would attract a positive, and a negative charge would repel another negative charges. Another way of saying that is like attracts, opposites attract, and like charges repel. Okay, so here's a couple questions. What happens to the freely moving positive charge when you look at this animation? It is doing what? And it's repelled away from the fixed positive charge. So this is fixed because it's stuck in a place it's not allowed to move. The only ones that are allowed to move are these two other charges that are being released. What happens to the freely moving negative charge? Take a look right here. What's going to happen to that as it's released? And it's going to attract towards the fixed positive charge, the one that's stuck in its place. And then why does this occur? This is because opposites attract and like charges repel. So what's the difference between electricity and current? If you take a look, this charge is stuck on that item itself, that thing itself, whereas this charge is a moving charge. It's going from one place to another. We call it a current. So when we have a static charge, what's created, so the field you see here, these are two different fields. I know they look the same the way that I made the animation, but they are different fields. The reason why I know they're different fields is because this charge is not moving, it's just staying there. So this field that's being created is called an electric field. Whereas this charge, as it's moving over and over and over and over, a moving charge creates a different type of field, and that's a magnetic field. And we'll have a future lesson, we'll look a little bit more into magnetic fields. But in this unit, we're going to look at electric fields and static charges. So look at the animation. How is a static charge different than a current? What's happening here that's different than right there? And static charge is not moving. It's just confined to that object. And then what kind of field is created by this charge right here? What's this field? And that's going to be that's not the answer here. What kind of field is going to be a electric field? And then this one right here would have a magnetic field, which is not a question on this slide. Okay, so let's take a look closer to an atom. When we look at an atom, we have a few things we have. We have a nucleus in the center, so this area right here is a nucleus. We have neutrons, which you can tell by I just put the little zeros, which means neutral, there's no charge on them. And then you have these protons. These protons have a positive charge, and the nucleus sticks to itself. Whereas outside of this nucleus, you have these electrons. They're just flying all over the place, and they're outside the nucleus. We often call these things orbitals. Where they are actually located, how they work. There's a little bit of a discussion about that. But for the sake of this lesson, electrons are outside the nucleus. The nucleus, everything in the nucleus is confined, but electrons you're going to see later on that they can be shared. Outer electrons can be shared with other objects. So orbits is just the outside where we call where the electrons are. And electrons have that negative charge. So there's a little negative next to it. If I drew it out, it has a little negative next to it, but it's too fast to see in this animation because electrons are just flinging all over the place. You need to know a little bit about the charge, and if you have an equation sheet from my class, you have this on it. It says QEL equals negative 1.6 times 10 to the negative 19th coulombs. This just means every single electron has a negative charge of 1.6 times 10 to the negative 19th, so that's 0.0000, a lot of zeros, then 1.6 coulombs. And the coulombs is going to be the unit for this unit for charge. When we see Q, we're actually going to see capital Q more often than the small q, but they're going to represent the same thing. It's going to represent charge, and the unit is going to be the coulombs here. Where in an atom do you find a proton and what sign is its charge? You are going to find it in the nucleus, and it's going to be positive. Where in an atom do you find an electron and what sign is its charge? It's going to be outside of the nucleus. So you could call it the orbital. If you said the orbit, that's fine. And it's going to be negative. And then here, given this information, an electron has a charge of negative 1.6 times 10 to the negative 19th coulombs. What is the actual charge of a neutral atom? So the atom was neutral after gaining 2 of these. And all you'd have to do is you take that number right here and you'd multiply it by 2, and it would have been negative 3.2 times 10 to the negative 19th as your answer. And I should have had coulombs. It should have C at the very end of it. And so one thing to really note here is when we have a charged object, protons are stuck to the nucleus. They're not really moving off of an object, whereas electrons are going to be freely moving, especially outer orbit electrons. And you're going to find some that can go from one object to another. So when an object becomes negative, it means it gained electrons. And when an object becomes positive, it means it lost electrons. No protons are moving in the making something positive or negative. So watch out for any sort of trick questions, and whether here or somewhere else soon. So we're going to look at friction, we're going to look at induction, we're going to look at conduction, 3 ways that things can be charged. We'll look at these individually. But first, before we just describe friction and charging by friction, what it is, we need to look at why friction is going to be important. And that's when we think about electrons, some things, and you think of positive and negative charges, how there's attractions and repulsions, negatives and negatives, positives and negatives. Well, don't think don't get too into this, but the main thing here that I need you to think about is that there's going to be some objects that want to hold on to the electrons more. We call that an affinity. Anything that has a greater affinity for electrons is going to try to hold on to it because it likes it more, and it will become negative whenever possible. And anything that has less of affinity or doesn't hold on to those electrons as much is going to have a tendency to lose electrons and become positive instead. Once again, electrons move towards to become negative because something sucks it in, or electrons are given off making something positive. It's all due to its affinity or its attraction to those electrons. And if you look at this list, the things at the top have a greater affinity to electrons than others. So if the most extreme, if you rub PVC against some sort of glass particulate board or something, the PVC would become very negative, whereas the glass would become very positive. And anything up top, when it's like rubbed with something below it, the thing on top is going to become negative, the thing on the bottom is going to become positive. For example, if I took silk and I rubbed it against hair, the silk would gain a negative charge, where the hair became gain a positive charge because those electrons were transferred over, and the charge itself would be equal. Whenever the hair lost in electrons, the silk would have gained in electrons. So the process of charging by friction, you take 2 objects, you rub them against each other, and the one that the electrons are just going to bounce. So if you take a look, electrons are going to kind of bounce off each other, end up in between the 2 objects, and then they're going to want to stick to one, and they're going to stick to the one that has the greatest affinity. Often you won't lose all electrons, you'll just lose some of the electrons, there'll still be some remaining, but the thing that has the greatest affinity is going to become negative, making the other object positive. So that's what's happening here. So here we have a PVC pipe that has a greater affinity, so it wants electrons more than cotton. And when you rub that PVC pipe against the cotton, well, the one that wants more, the PVC pipe is going to take on those electrons and become negative. And the actual cotton would become positive. For tan, hair has less affinity, so now it's telling you it doesn't want electrons as much than wool. So wool has a greater affinity. Would your wool hat or your hair become negative? Well, it's going to be the wool hat because it's the one that wants electrons more. A neutral cotton cap is on your hair. Your hair is left with a charge of the positive 1.776 times 10 to the negative 13th coulombs when it was removed. Well, the resulting charge on the cotton cap, that charge, those electrons that came from this and went to the cotton cap, so therefore it's going to be the opposite. It's going to be a positive 1.776 times 10 to the negative 13th coulombs. And if you put those 2 numbers together, add them together, it should be 0 again, because they were initially neutral and one got a charge, and it got this charge by giving off electrons to this guy over here, the negative 1.776. Which of the following occurred when a neutral PVC pipe was rubbed up against a neutral cotton cloth, giving the PVC pipe a charge of negative 2.96 times 10 to the negative 13th coulombs? Okay, so the PVC pipe got this charge. So what happened? Did the PVC pipe lose protons? Nope, can't be. Protons aren't going to move. So that's not going to be the way that this got the charge. PVC gained protons. Once again, it doesn't matter. Protons aren't moving here. Electrons are moving. So let's find out which one of these are right. Well, if it gained a charge of a negative, it must have gained electrons, and therefore the answer here is going to be this last one. And now we're going to look at the actual quantitative charges. And so we're going to use this. If you're a proton, you're going to have a positive charge like this. If you're an electron, you're going to have a negative charge like this. And there are going to be a few questions with those. And anytime we want to find an overall charge, we just multiply the number of particles times the charge, whether it be positive for protons or negative for electrons. What's happening in dryer that may lead to static cling on clothing? So this is a dryer at home. There's a lot of different materials in here. There's wood, there's wool, there's cotton, there's all different materials. And not all of them stick to electrons the same. So especially on a dry day, in a drier day, electrons don't transfer away from objects as much. A drier day, when you wash your clothes like this, they get real dry. The ones that have a greater affinity are going to have the negative charge, and the ones that have less affinity is going to have a positive charge. As a result, both positive and negatives are going to have static, there's going to be some sort of static cling. We'll see a little bit later induction and how that could result in static attraction. The charging by friction in material with different affinities for electrons rub together, causing this. Simple and sweet. You comb your hair on a dry day. The comb gained 2.3 times 10 to the fourth electrons. Each electron has a charge of negative 1.16 blah, 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 times 10 to the negative 19th coulombs. What's the charge on the comb? You're just going to take that number, your number of electrons, multiply it by the charge for electrons, and you would get this, negative 3.68 times 10 to the negative 15th coulombs. What's the resulting charge on your hair? Well, it's just going to be the opposite, because these have to be, if they were neutral, when you put these back together, you'd end up with a 0 coulombs or a neutral object again. So whatever one gets, the other one lost the electrons, and therefore it's going to have the positive charge. Electrical insulators are materials where electrons don't flow freely. So here you have a wire and you have an insulator where electrons aren't going to flow. They're going to flow all over the wire very quickly. We'll see that a little bit later. And this insulator, electrons don't flow very easily. So this person can grab the wire, and when they grab the wire, electrons aren't flowing from the wire and then going through the person to the ground. You'll see grounding a little bit later on as well. And the person gets electrocuted as a result. That's not going to happen. So the insulator is going to be a very useful thing for electronics to avoid any sort of electrocution where from the electrons flowing that would flow through the conductor. Insulators are used for wire coatings and protective gloves. Common electric insulators are rubber, plastic, glass, and even the cheapest one is air. And then wood is another insulator that can be used to try to avoid maybe a current that's flowing through a wire. Electrical conductors, which metals are included. You can have like superconductors where certain things happen, or semiconductors. There's a bunch of different conductors. But for the case of this lesson, we're going to talk about metals. Materials which have freely moving electrons. So take a look. These electrons are all over the place, pretty much shared everywhere at once. Electrons are kind of strange, just everywhere. Freely moving electrons are valence outer electrons. Which move independently from the individual atom. So some electrons, when we remember the atom, there's going to be different orbitals, and some of these outer orbitals, whatever the last orbital is going to have, there's a few extra electrons, and those are electrons you see here. So there's still some electrons stuck to these individual atoms, but some of these outer electrons are just shared throughout. Wire metals, when they're going to act independently, they can actually transfer off of this object, and they can transfer onto the object, giving and taking away charge. And so that's what the whole independent movement means. Wire metals good conductors because of how they transfer electrons, how quickly these electrons go from one place to the other, pretty much are everywhere. And we call it this an electric cloud. There's an electron cloud model because if you take a look, it looks more like a fuzz than actually seeing something in one place. Some of the top conductive metals are silver, copper, gold, aluminum. There's reasons to use something like a copper cheaper. It doesn't tarnish as much, creating a less conductive surface. Copper is one of the most useful conductors at a decent price that we have. We often use in our wires, but we can use, especially if you have a little bit of extra money, you might want to use gold. There's reasons for using each of these. Now, when we have similar conductors, now, like I said before, when you have a conductor like this one, take a look at the first object, it's charged, the other ones are neutral. As soon as they touch the next object, those electrons are shared equally, and those electrons want to get away from each other. So the charge is split. If these two were equal conductive metals, let's say they're copper and copper, well, as soon as they touch, the charge is split in half between the two, and then once it's released, the second one goes and hits the next one, and that charge, once again, is released in two. If the three objects were just touched together all at once, you pretty much, and then released from each other all at once, you would have kind of a similar situation, but you would have a different result, because each of these would have a third. But just look at the first one, cuts in half, and that's the result that you see here. So what is the new charge on this -6 times 10 to the -6 Coulomb charged conductor after separating from a neutral, after touching and separating from a neutral conductor of equal composition? So it's just talking about this first part. What's the charge here after it touches? And you can take a look. It is this answer right here, half of it, just the first part. It's not talking about the second part of the contact. It's going to be -3 times 10 to the -6 coulombs. It says you have a charge on one object of that -3.6 times 10 to the -7 coulombs, and when another object comes in and touches it, they're going to initially share that entire charge, so combine 3.6 times 10 to the -7 coulombs. But once these two objects separate, they're each going to take half the charge because the electrons are going to want to stay as far away from each other as possible, these extra electrons causing this charge. And so as you separate, you're going to have this right here. So your answer is going to be half of what your initial value was. Each of those objects would have had -1.8 times 10 to the -7 coulombs of charge. So just a reminder, we said this before, like charges, positive charges repel positive charges, negative charges repel negative charges, opposites attract. Kind of started off with that. What interaction, attraction, or repulsion occurs between a negative and positive charge? If you take a look right here, there's going to be an attraction. So just a little review from before. And then now there's just more of a tricky question. Let's go ahead and see how this works. If ball 1, so these are all separate interactions. So these are not together. And the only thing that happens here is charge 2 is going to be the same as whatever this. This is the same ball. It's like I took it out of here and put it in this situation. So you just ignore everything. Think about the first interaction. If the first ball was charged negative and it was repelling, see how they're pushing away from each other from the second ball? Well, what charge would the second one be? And that would be negative. So now let's go ahead and let's ignore that first situation. Let's ignore that altogether. Let's ignore this one. We know that this is negative based on what we said before. Well, if that is negative and it's repelling 3, what must 3 be? And 3 would also be negative. So let's go ahead and take that charge. Let's move it over here. Let's ignore all this. We're no longer considering all of this. We're looking at this 3, and it's attracted to 4. So what charge would 4 have to be? And that's going to be positive right here. Another question. An object A and C are equal distance from the positive charge B. Which of the following would create a net force on B to the left? So we want to find out which of these situations would cause B to want to go to the left. If A and C were both negative, if A was negative and C was negative, this would want to go equal, and they were equal to each other. This would not want to move because it would be equally forced both ways. So that's not going to happen. If these were both positives, A would cause B to go right and C would cause B to go left, but if they were equal, that's not going to happen either. B would not want to move. So neither of these are going to work, and I think I have lines that show it. Okay, let's take a look at the next one. If A and C were both positive, and the charge on A was greater, so this was more positive. Both positive. The charge on A was greater than C, so this is more positive than C. C is just a little bit positive. Well, what's going to happen is this one is going to have a greater force on B to the right than that one, and so B is going to want to go to the right, so that's not going to work either. If both were positive, but C was a big positive, C is going to repel that B. It's going to want to go to the left. This is going to push it to the right, but not as much as C, so this would be a situation where B would move to the left, have a net force to the left. If A was positive and C was negative, A is going to want to push B to the right. C was negative, C would want to push or pull B to the right, and it would be a left overall, so that's not going to work either. If A was negative and C was positive, A would attract B, and C would repel B, creating an overall net force to the left. And so those are the two possible choices out of all of these in this situation, the way it's asked. Okay, so let's finish off the lesson looking at charging by induction and charging by conduction. Induction, what's happening here, what you want to see here is you have an object that's charged and it's being brought close to a neutral object. So take a look when this negatively charged rod is away from the sphere. The electrons are all over the place. There's equal negatives to positives. You can't tell unless you count them, but just believe me on this. There's equal negatives to positives, and this object's neutral. But when the negative charge comes close, the protons really don't move very quickly. So the positives stay where they're at. The negatives get pushed away, leaving a positive charge. So what's happening here by induction, you have no contact. You have a negative charge inducing an opposite charge. And we would call it temporary because once this negative rod is being brought away, the electrons return because they want to spread out as much as possible. And this becomes neutral overall. Take a look at this positive charge. Same thing happens, except electrons are attracted. So this positive creates this negative side while it's close, and there's an attraction as a result. No contact, there's no actual flow of electrons, so it's temporary because electrons are going to flow right back to where they were before. So charging by induction effects, no contact, opposite charge is induced, and it's temporary because there's no transfer of electrons. Another way of saying what happens, the positive would induce a negative would induce a positive, just like you see in this animation right here. What subatomic particle moves to create a charge? It's going to be the electron. Is there contact between the pipe? Is there contact between the pipe and, let's get rid of that, and the metal sphere during the induction, and there is no contact? Do the electrons get transferred during induction between the charge and charging object? And there's no, they just stay on this object the whole time. What charge is induced on the closest object to this PVC pipe? It's going to be positive. See how the positives left over as this gets close. Charging by conduction. So charging by conduction, you have an actual transfer of electrons. So this object's really negative. And so these negatives are going to want to jump off the object if it's brought close to a conductor. This is an insulator, so they're not going to all jump off like they would if it was a conductor itself. But a few of these electrons are going to jump onto the sphere, making the sphere also negative. So here you have contact, you have electrons transferring, and when they transfer, they actually leave the PVC pipe. So it's a more permanent thing until grounding occurs. These electrons are going to be stuck on there until something allows those electrons to leave, like being in contact with something that touches the ground. The ground is a universal just acceptor or giver or taker of electrons. If something is charged and it touches the ground, it's going to suck up that charge and make the object neutral again. So charging by conduction, you have contact. Right here, contact. You actually hit that object. It induces the same charge. Notice how this becomes negative from a negative object. And it's permanent because there's actual transfer of electrons. Negative creates negative, positive creates positive. Let's answer these questions. What subatomic particle moves to create a charge? That's going to be an electron again. Does the pipe make contact with the metal sphere? Yes. So think of C for contact, conduction, contact. Where do electrons come from? They're going to come from the negatively charged object. And what charge remains on the neutral metal sphere after the contact? And it would be negative if this was negative. If this PVC pipe was positive, it would actually suck off electrons, leaving a positive charge. So like a positive PVC or pipe of some sort, maybe a glass pipe, would suck off electrons, making this a positive would create a negative as a result. A negative creates a positive pipe would create a positive here as a result of sucking off the electrons if this was a different situation. But plus creates plus, or plus creates plus, negative creates negative in conduction with contact, for C for contact. Lastly, grounding. So if you do have a charge, this is how lightning works. The ground will accept. The ground has unlimited electrons, protons. The electrons can go away, leaving a positive charge, taking on electrons. Whenever you have lightning, if it's lightning, the weaker lightning is negative strike lightning. Electrons flow to the ground, so electrons actually transfer to the ground. It's a lightning bolt downwards, and that's going to release. It's going to relieve the extra charge, making the cloud neutral, or at least neutral-er, depending on how charged up it is. And that would be negative strike lightning. Positive strike lightning is much more dangerous because you have charges, you have electrons coming from the ground to the top. Those negatives will relieve the positives, making the cloud neutral as a result. So the positive strike lightning is actually reverse. It goes from ground up. And that's super dangerous because you need a lot of charge. This has to be a really, really huge charge for it to create that lightning strike. We'll see in the next unit with Coulomb's law that you need a big enough force. You need a really big charge to allow lightning to go upward because of the distance it has to travel. Negative strike lightning downwards is much easier because it's a much less of a distance for the actual electrons to travel